Hello everyone. So today we're very happy to have Faulkner, who's here just today.
Yeah.
Today. Okay. So your office is somewhere here?
Right there.
Right there. So seek him out. You want to talk to him? He's going to give us a talk on quantum error correction at large N for quantum gravity. Take it away.
Okay. Thanks, Ahmed. Thanks a lot for having me. So I'm going to tell you about a story. So the main framework was written down in this paper by student Min Lee, and then there's several papers in the works that are sort of using these ideas. And the basic idea is the following. We want to connect two main ideas for studying holography and gravity. In particular, this quantum error correction paradigm for gravity that Ahmed introduced in this very famous paper, EDH. So this is a broad collection of ideas that has had a lot of success, explaining things like the Takinagi formula, entanglement wedge reconstruction, and then because of that, the black hole information paradox, some new insights into the black hole information paradox have come from this. Another broad area that has had a lot of success lately is studying something called gravitational or Neumann algebras. This has also had a lot of success in studying things like black hole entropy, even the entropy of cosmological horizons like de Sitter space can be understood using this sort of language. And the goal of this talk and this sort of program is to connect these two. So to put this in particular these von Neumann algebras in the language of quantum error correction. So I would say the broader goal of this program is to find some kind of axiomatic framework for the emergence of semi-classical gravity from quantum mechanics. So if we have some quantum mechanical system that satisfies certain properties, then we can use some framework to study the emergence of gravity. And the idea is the framework will be something like this. It's not going to be this. There are things that we still need to do, but I think this is a step in the right direction. Okay, so let me sort of explain these two things first, and then I'll explain how I'm going to combine them. Okay, so we'll call this A and B, and we'll start with A. Okay, so firstly, there is some expectation from holography that when we have like a black hole horizon, or even some kind of, maybe more controversially, but some kind of cosmological horizon, then there should be a way to describe that using some quantum mechanical system with a number of degrees of freedom that go like the Bekenstein-Hawking entropy, or the appropriate entropy for the cosmological horizon. So that means that there's some Hilbert space, and the dimension of that Hilbert space is EVS. Okay? So for example, in the black hole context, if I have some black hole, some stationary black hole that has two universes like this, left and right, and this is the killing horizon, then this should be somehow dual, or at least physics that's close to the horizon somehow, should be dual to something, some thermophile double state in some discrete quantum Hilbert space. This. So this is some state that lives in a Hilbert space, kappa left, kappa right, and the dimension of this guy, of one of these, is EVS. Good. But from this point of view, if I look at this Hilbert space, this is a pretty standard quantum mechanical thing. In particular, the observables that you would associate to the right part, observables, are pretty good, when you think about those observables are operators, bounded operators on that Hilbert space. So we write that B of kappa R. Okay? We think of this as some kind of subalgebra, if I tensor in the identity on the left, as some subalgebra of all the observables that we have. Okay? And when you have a subalgebra of this form with a tensor product here and B of H, then this is what we call a type 1 factor. So this is a type 1 von Neumann algebra. And it's the thing that we kind of expect this system to be dual to some finite dimensional quantum mechanical system, and that will always give you type 1 von Neumann algebras. Okay? However, this is kind of incompatible with what we expect for physics near the horizon. And so for physics near the horizon, we expect quantum field theory to be a good approximation in some limit. And quantum field theory has all of its states have a large amount of entanglement on all scales. Right? So if I keep zooming in, I still have entanglement. And that means that we no longer, you can provably show that it's no longer described by a quantum mechanical system like this. In particular, it has to be something like, there's some Hilbert space I'll call H, and then there's subalgebras, A left and A right, that we associate it to the left and the right. They're just subalgebras of all possible operators, P of H. So that's like, this is a subalgebra of all possible operators that acts on this total thing. In particular, because of this sort of fact that these states are entangled on all scales, that means that you can also prove that there's no such thing as a maximally mixed state, or even a non-normalizable maximally mixed state. And in that situation, you can show that AL or AR is a type 3 von Neumann algebra. So this is part of the classification of von Neumann algebras. We really don't need to know much about this beyond what I just told you. Okay, so these things don't have sort of maximally mixed states or even non-normalizable maximally mixed states. Here, the maximally mixed state is just this sum where I strip off this factor. Right, and so this is type 1. It could have also been type 2, which is another example where you have maximally mixed states, but it's not, because then you don't have tensor factorization like this.
So Tom, when you say maximally mixed, you mean maximally entangled, like it's still a pure.
Well, yeah, so I mean just like the eigenvalues here are the same, right? So it's something like that, I'm being very schematic with these definitions. The right thing is to talk about traces on the algebra, but I'm not going to go into those details. I just want to give you some flavor, so this distinction. Okay, so everyone happy with that? So we have quantum field theory here, and we necessarily have this other kind of von Neumann algebra, so we have this sort of this issue, right? All right, okay, but of course, a few things to say. So firstly, you expect, okay, this is only valid on some scale. So it's effective field theory, there's some cutoff. So at that cutoff, of course, there should be some new UV physics that maybe we don't really understand, but when we include that new UV physics, we should get back to this. Right? That's the expectation. But then, yeah, good. So in particular, yeah, there's lots of evidence for that. But we would like to understand, we would like to have a framework where this kind of thing can emerge out of this kind of thing. And in particular, the framework that people have realized is that if we take this, the G Newton goes to zero limit seriously, then that's something where we can sort of have this transmutation of algebras. Okay, and so good. So so the idea in this approach is we take the continuum quantum field theory seriously. So we take continuum quantum field theory seriously. We imagine it's arising from a limit. L Planck goes to 0 or G Newton goes to 0. And then maybe we can start there and do perturbative corrections in that approach. And so when we do that, the first thing we notice is the black hole entropy with a formula which I didn't write down, the area over 4G Newton. in these sort of limits, we're imagining holding the area fixed. So the black hole entropy goes to infinity. And indeed, that's what we expect, because when we're in a type 3 setting like this, there is just no way to assign an entanglement entropy or an entropy to this algebra here. Okay? And so the answer is sort of infinite. That's the entropy. All right. And so in this limit, we expect emergent von Neumann algebras. And in particular, so this is what I refer to as gravitational von Neumann algebras, and the starting point for this were these papers by Liu Leuthauser, and then it was picked up by various people, CPLW, Chandrasekharan, Pennington, Longo, and Witten, and various combinations of those authors. And this is the basic idea. So we take a large n, then we take a small g Newton limit, and then we expect in that limit to have some emergent von Neumann algebras. There's more to this story. I will just mention briefly. If you include gravitational dressing effects, then there's a new thing that happens. In particular, you want to include the fluctuations of the ADM mass of this black hole. If you do that properly, you find that the algebra is no longer type 3, but it switches to something called a type 2 von Neumann algebra. Type 2. And that's an algebra, as I mentioned, that has these sort of maximally mixed states, or this analog of this maximally mixed state. And in particular, in that setting, you can actually define an entropy. You use the maximally mixed state to define an entropy. And so there's some notion of entropy, and that's interesting because maybe that's what we should think of as the black hole entropy. Really, what you should think here is the black hole entropy is still infinite, but this is what you get after you subtract off some infinite constant, get this type 2 entropy. And this actually has meaning because you can do this for multiple states and take their difference and then get rid of this infinite constant. Okay? Yeah.
I don't understand the meaning of the word emergent,
Yeah.
because it's not that it came from nowhere, it's kind of curious if I understand correctly, it's the limit of the type 1 thing, right?
Yeah.
So,
Well, I would call that emergent because it starts off as type 1 and then it becomes something else. So it emerges. So maybe that's the wrong.
but it's more like there's some limit when the type of Neumann algebra changes. Right?
Yeah, that's what I mean by emergent. But yeah, maybe you're not happy with that language, but yeah.
No, I understand.
Yeah.
I understand exactly.
Yeah, that's what I mean. Yeah. Okay, good. And so in this setting, we have finite von Neumann entropy, but we still don't have factorization. So the Hilbert space is not a factor. It can't be written like this. And so we still, to really understand what's going on, we should somehow figure out how to go back to this type 1 setting. And so what I'm going to talk about today is some framework, not really where we try to get back to the type 1 setting, but where we really try to understand how this limit works. So we want to understand how the limit, where you have these potentially type 1 von Neumann algebras, and it becomes something else in the limit. Okay? And the way it turns out to do that is to go back to this this picture of quantum error correction. So we combine these two things. Okay, so that leads me to the quantum error correction side of this story. Any questions about this so far? Okay, so B. So B. When we're thinking about quantum error correction as some model of ADS CFT. Often you'll see toy models of what's going on with this, right? So we have some toy model of ADS. So you'll, in particular, usually it's some kind of tensor network. So let me draw some tensor network. So we have some tensor network where we have sort of boundary vertices. They're connected to some bulk vertices in some random way. Like this. These are bulk vertices. And then we have some out of plane legs that I'll try to colored chalk there. Yeah, I'll just dash. Out of plane legs, like this. And so this is meant to be some kind of model of ADS-CFT. In particular, you should think of the boundary vertices as being the boundary Hilbert space. And then the bulk, the out of plane legs are the bulk Hilbert space. So this becomes a map. So this is a map V between two different Hilbert spaces, H to kappa. So H is the Hilbert space associated to these out of plane legs, and kappa is associated to the Hilbert space on the edge. Okay, and so this tensor network picture defines this map. Usually to do calculations, we'll pick these tensors to be random tensors. We have to make some choice, but if you pick them to be random, then you get nice results. And so instead of drawing this kind of complicated picture, I'll just draw a picture like this, where we have some kind of Hilbert space H coming in, and then kappa coming out. Like this. Good. Right. And additionally, you show that this map satisfies nice properties. So in particular, approximately V dagger V is the identity. So that defines this map as an isometry. Yeah.
K is the boundary.
Yeah. So this is so this is my bulk Hilbert space, and this is the boundary Hilbert space. Okay.
So in that tensor picture down there, you should have more legs on K than in H. Roughly speaking.
Yeah, so I don't really care how many legs I have, they're just random Hilbert spaces. So yeah, this is meant to be just this is some schematic picture of this. I'm going to break this up in various ways. Yeah, so, and the other thing is, these legs don't have to have any particular dimension. So yeah. Good. So good. So yeah. Now in this case, you can prove things like something analogous to the RT formula. So in particular, if you want to compute the entropy of some boundary regions here, then the rule is to find a minimal cut through this network and compute its area, which is just the sum of the legs here, and log of the bond dimension of these legs. But there's some minimal cut through this surface that computes through this network that computes the entropy. It looks like the RT formula. It's sort of valid as the bond dimension, so that these things have sort of internal bond dimensions. As chi goes to infinity, or you can think of as G Newton as roughly 1 over log of chi in this setup. Okay. Good. Now, it's an important feature of this sort of. This is just the RT formula, but you can understand this map as some kind of quantum error correcting code. So we draw a picture like this. V takes a complement, big A. Right, so this is the bulk, this is the boundary. And in particular, A and A complement are the region we want to compute the entanglement entropy for. Get rid of this. And then associated to that region is the cut, right? So we have this cut, and then if we label all the out-of-plane legs that are inside the cut as little a, and all of the out-of-plane legs that are outside the cut as a complement, then this splits this Hilbert space into two, right? So that's denoted by this Hilbert space. So like this, and this is K, a complement. And the idea is that this RT surface sort of delineates where I can reconstruct the information in the bulk from the boundary, right? So in particular, we associate little a with big A if there exists some map that takes bulk operators, so operators here, to operators in A. So this is some operator that goes from phi A to OA by this beta map. such that it sort of reconstructs its action on the code. So you write down an equation like this. Right, so if you want to act on A, like phi A, then this is the thing that does it. Okay, so this is called operator reconstruction, and it's sort of the thing that associates the bulk region, little a, to the boundary region, big A, right?
Can I think this as a bulk boundary propagator in the classical idea CFT? Like I move in Poincare coordinates in Z, and I should get a conformal two-point function in Minkowski force, something like that, that brings me one operator in the bulk to one operator in the boundary?
Yeah, so yes, there's a sense in which this thing, in some limit, looks like the usual extrapolate dictionary of gravity, yeah. But it sort of goes beyond that, because the extrapolate dictionary is somewhat limited by causality of the bulk, whereas we'll see this entanglement wedge is beyond the causal wedge. So it's beyond the things that you can usually influence causally in, with just bulk physics, and the extrapolate dictionary is something that usually just does that. So it's a little bit beyond that, yeah. Okay, so this is called operator reconstruction, and this is for A related to big A, and if you're in a situation where A is related to big A and A complement is related to A complement, which is the setting here where you have some RT surface like this, then you can prove that this is equivalent to the RT formula. So knowing how to compute entropies in this setup using the RT formula actually means you can do operator reconstruction. So there's some correspondence that's a proof of this. Okay, so questions about this? All right, so let me make a few comments about this. So the first one is that it's only in this setup, especially the random tensor network setup, where this is true, at least for a large bond dimension, it's only approximate, which means things like V dagger B is not really the identity, but it's close to in the operator norm. So this is approximately 0. So you can do many things. So this is sort of usually thought of as somewhat necessary for quantum error correction, although recently there's been work doing non-isometric codes where this is not the case. But traditionally it's been thought that that's important. Yeah.
Error is exponential in homogeneous, is that correct?
In this model, yeah. Yeah, that's right. Yeah, it's like the difference in the total dimension of these two Hilbert spaces, yeah, basically. Yeah. Good. Yeah, good. So, yeah, so that's only approximate. This tensor factorization is not very realistic for quantum fields in the bulk, which is maybe what you want, right? So in fact, there was an answer to this already in Ahmed's original paper where they didn't talk about these kinds of tensor network picture. They just sort of constructed a code directly from what we know about ADS CFT. And then the idea was we have ADS, which I'm just drawing a time slice through, which is like this sort of tin can picture. And then we just act with some finite number of operators. And with those operators, we construct some Hilbert space, which I'll call HP, which is basically the Hilbert space you get by acting with these fields, and then the linear span of all of those things. And it's some kind of projection of the actual Hilbert space. So the actual quantum field theory Hilbert space, you need to project to this sort of the part of the Hilbert space you get by doing that. Good. Okay. And so in that case, Ahmed and friends proved that you have some kind of quantum error correcting code that works like this. Okay. All right. So that seems to solve maybe this problem. But I would argue there's still a few shortcomings here that we'd like to fix. some shortcomings. So firstly, how do we pick the subspace? There's some random choices we made here. That's just a choice. Maybe we don't really want it to depend on that choice. So you maybe want a framework where we don't have to make that choice, or something which doesn't really matter what we choose. The other issue is that the fields that you would act with here, the bulk quantum fields, they don't really form an algebra in a traditional sense. Basically, because if you act with enough of these fields, then you might create a black hole. And a black hole is usually something you don't want to include in this picture. Right? So you have some quantum error correcting code that works for some subsector of the theory that wouldn't maybe necessarily include a black hole. Yeah.
I think we addressed that in the paper by saying you take all these operators and you conjugate them with a projection.
That's what I'm about to say.
Okay.
But you can truncate, and that's okay with this P. That's what I meant by this projection. But then maybe there's some questions of locality. Like what happened to locality in the quantum field theory under that projection? That projection is not obviously a nice thing. So maybe we want to preserve this locality. Yeah. Okay. And then the other thing is dynamics. Dynamics has often been tricky for these quantum error correcting codes, especially if we go back to this toy model. This toy model has no dynamics, just a map from two Hilbert spaces, one Hilbert space to the other. You would maybe want to have a Hamiltonian on the boundary, a Hamiltonian in the bulk, and maybe they're related. And there are some papers that do that, and that's interesting, and there's some interesting results there. We're gonna have a different approach. And then other quantum field theory aspects missing, such as causality, locality. What I've always been looking for is some notion of energy conditions that we can trace through the dictionary, and it's not obvious how to do that. And another big thing, which I won't write, is just related to sub-ADS locality. What happens if the bulk theory is not really local, it's a string theory, can we still use this framework? So is there some difference between the case where you have a string theory in the bulk and you don't? So let's try to fix some of these. So fixes. The first thing I'm going to do is have some quantum field theory like bulk Hilbert space. Right, so my bulk Hilbert space is now a quantum field theory like Hilbert space. And what I really mean by that is that when I restrict to some regions like this, I no longer have a tensor factorization. And I have to go back to this sort of von Neumann algebra picture where the algebra of operators I would associate to some region is some subalgebra of all possible operators that's type 3. Okay, this is what we expect in this setting. It should be a type 3 von Neumann algebra. But something that comes along with this, and something I didn't say, is as soon as we're beyond type 1, the dimension of the bulk Hilbert space has to be infinite. Okay, so now we're working with an infinite dimensional bulk Hilbert space, which is quite different to these sort of error correcting codes. Okay, and so this is part of the fix, but we have to do something quite different now, because if you think about it, we have to treat errors differently. So, and this is kind of the main point in our paper, and the thing that we sort of solved. So we have to treat errors differently. And by errors, I don't mean like, the standard errors in quantum error correction. I mean like of the approximate nature. So this means it's an approximate nature. So you have to treat these approximations slightly differently. Good. And so the idea is that we have to use a different notion. So this thing, v dagger v minus 1, is close to 1. It means that v dagger v is close to 1 is small. It means that it's sort of uniformly close to 1. So this is another way of saying it's uniformly close. Uniform just means that acting on all states, it's always close to 1. Okay. Instead, so this is uniform. Instead, we're going to use a different notion. We're going to use pointwise. So pointwise is going to mean that in fixed matrix elements, this is close to 1. This is small. But not necessarily as an operator. And so I'll clarify, this will become clearer when we actually write down what we're doing, but there's going to be a distinction between these two. Okay? Okay, and so our codes are going to be somewhat pointwise. They're not going to work on all states in a uniform way. They're only going to work on some set of states. But what set, and why? Is there some distinguished set? And the answer is no. But as long as we treat the large n limit as part of our code, so we're going to incorporate the large n limit, right? Which you should think of as the small g Newton limit. So in all of these models, g Newton goes like 1 over n like this. So we want to take the small g Newton limit as this von Neumann algebra discussion suggested, and we want to now incorporate that into the actual code. So how are we going to do that? Well, we're going to have a sequence of Hilbert spaces that I'll call kappa n, and these are the physical Hilbert spaces. These are the microscopic Hilbert spaces. So if you like anything with an n on, it means it's microscopic or physical. We're going to have a code Hilbert space that is the same for all n. So we're going to use this as a code for this. This is going to be the same for each n. And you maybe should think of this. One way to think of it is it's like the n is equal to infinite theory. And that I'll make that a little bit more precise. But basically it's the same for each n. And another way to say it is that, well, okay, if you wanted to do perturbation theory, you better get the n equals to infinity, say in 1 over n, then you better get the n equals to infinity part of that under control first, and then you can start including 1 over n corrections. But it will be based about this description, okay? And so that's what this is. And so it's sort of effectively the same for each finite n. And then we have a sequence of maps that takes us between the two like this. Okay. And then we have various properties of these maps that we'll write down. Yeah.
Regarding the uniformly closed case,
Yeah.
wasn't that too much to ask? Because the properties of the map depend sensitively on the state.
Yeah.
Because V depends on the state.
Well, yeah. So there's, okay. So I'm not going to ask this, right? So,
Yeah, I know. I'm
yeah.
saying it's too unreasonable to have expected.
Yeah, well, that's another way of saying it. I think it's a slightly different notion because the thing that I'm going to have is still going to have state dependence. So the bulk Hilbert space, this will be state specific in some sense. Yeah. So that's right. But yeah, I think, right. But in these toy models, this is approximately true. In your code, in your truncated codes, this will also be true. This is still good.
It's true within that subspace, but it's not true.
But that's what it means, right? So this is taken in that Hilbert space, right? And so you're saying, well, project and then it's fine.
Yeah, if you project that, then it's fine.
Yeah, that's right. That's right, and I agree with that. Yeah. And so a sense of what we're doing here is that this is one way you can understand this is that now you can take this Hilbert space and project, and you'll find exactly what you found. But you didn't have to do that, right? So there's no there's nothing special about any projection, any given projection. Yeah. So that's one way of saying it. Good. All right. Yeah, so I agree. All right, so in this context, so we have this sort of sequence of maps. We want to understand what it means to do quantum error correction. And so for that, it's useful to prove a theorem about quantum error correction. And I actually forgot to mention it when I talked about it here. So let me just state it really quickly. So if we go back to this sort of toy model of a tensor network, there was this reconstruction condition, that you could do operator reconstruction. You could write a bulk operator as a boundary operator like this, and it works. There's an equivalent way of writing this, which goes under the name of Knill-Laflamme conditions. It has other names as well, information disturbance trade-off, but you can either demand reconstruction, or you can demand that any errors in this case are associated to the complement of the code. So we write an error as some operator that acts on the complement. If I take that and I project it to the code like this, then this should commute with any operator phi a. So if you have this or this, they're equivalent. So these two things are equivalent. And this is called, sometimes called information disturbance trade-off. It's basic to the theory of quantum error correction. It's also basic to the theory of quantum mechanics. It's some version of no cloning, right? So you can think of it as you can't clone information, and this is the reason, in these codes you still can't clone information. And so this thing, which, there's many papers proving various versions of these things, we're going to prove one more version of these things in this context, where we have this sort of sequence of codes. And to do that, we need one assumption. Is reasonable.
Oh, there's a question?
Yeah.
So just in this pointwise convergence.
Yeah.
It looks like the way you've written it, it's just the diagonal elements that need to be small? Or
Yeah, sorry. That was a typo. That's meant to be some other function. Yeah, sorry. But actually, the way I've said it doesn't make total sense right now at this point. We have to incorporate it in the limit. So let me say it now in a different way. So the pointwise convergence that I'm talking about is, so we need pointwise isometric code, which means, okay, Vn dagger Vn should look like the identity in the limit as n goes to infinity. That's what we mean. Usually these codes are only ever approximate at finite g, what would be g Newton. So in any case, we usually have to take that to be small. So in the limit, this should go to 1, but how does it go to 1? Well, if I take matrix elements, fixed matrix elements, and I take the limit, I will just get this overlap. And so that's this notion of pointwise. And it turns out that in infinite dimensional Hilbert spaces, if you have this, it does not imply this. So in some sense, these codes are non-isometric. You might say this is the isometric condition, but they're only because you only demand pointwise convergence, you don't have this.
But phi and psi can be any state.
Yes, phi and psi can be any state, but they can't vary with n, right? So if they could vary with n, you could turn it into this. So the important point is that you fix the states that you want to work with from the get-go, and then at sufficiently large n, they'll work. The code will work for them. Yeah. And that kind of makes sense from a gravitational point of view. If I act with too many operators, I might form a black hole, but then if I send g Newton to 0, it won't be a black hole, it'll be a graviton, again, some gas of particles. It's sufficiently small g Newton. So that's sort of how we're solving that problem. Okay. All right, so good. So in this context, we want to prove some like information disturbance trade-off, like theorem, and so that's what we did. So I'll call this theorem 1. So it's a little complicated, but let's go through it. So this pertains to sequences of algebras, von Neumann algebras, which are sub-algebras of all possible operators in the microscopic theory. So this is analogous to this big A. So this Mn is going to be analogous to all of the operators that can act here. So this theorem pertains to those sequences and some bulk algebra like this. And so this is analogous to big A. This is analogous to little a. Right? For these two things, the following are equivalent. Right? So 1 implies 2, where 1 is some kind of operator reconstruction statement, which goes as follows. There's a sequence of operator reconstructions, beta n, that take you from the bulk operators to the boundary operators, that such that they reconstruct pointwise. So Bn of phi minus Vn phi goes to 0 in a pointwise sense. Same idea as this going to 0. Okay, so it works in a pointwise sense. And then the other thing is, for all sequences of errors, xn prime, that are in the commutant of n prime, so the commutant is just all the operators that commute with mn, so that's analogous to A complement here. Then if I project Vn dagger xn prime to the code, and I commute it with some operator n, this goes to 0, again, pointwise.
Can I ask you something? Maybe I should have asked it before, but we have some operator that takes states in H, but do we even know what are states of quantum gravity? Do I know what a psi or a phi is, physically speaking? Or let's say I imagine I know quantum gravity exactly by some theory, and I use those states, but we still don't know what that is, right?
Yeah, but that's not what I'm talking about. I think what you want is that. So that's like if I really knew all the states of quantum gravity and I could solve quantum gravity, then that would, I think, mean I could solve it at fixed G Newton. Okay, that's way too much to ask, but if I could, then I could write down this Hilbert space. Okay, but in ADS-CFT we know that Hilbert space is n equals 4 Sibelius Mills. So in some sense we've solved it. Okay, yeah, someone has solved it. So then what is this? Well, this it turns out is very physical. It's something you can construct. Basically, you use the single trace fields. So you want to take a large n limit, and I'll say a little bit more about that, but you use the single trace fields and a large n limit, they give you a Hilbert space.
For gravity.
Yeah, for gravity, that's all we're trying to get at this point, which is probably something I should have said. Effectively, because we're taking the strict large n limit, we're just talking about fluctuations about some fixed background. Small fluctuations around some fixed background. Yeah, and so that's why it's sort of state dependent. Ultimately, we want to do that about many different backgrounds and somehow patch them together, but we haven't done that yet. But yeah, so that's the idea. Yeah.
For this theorem, do you have to go all the way to the weak topology, or could you use the strong topology?
Yeah, so this is the weak topology. I avoided using those words. Yeah, so this converges in the weak topology. You could have, assuming the strong operator convergence of this is a stronger assumption, and of course it will work for this theorem. It's just that we could still prove the theorem with this assumption. So there's no particular reason which one is the right one. It's just that we could use this, and that's fine. So for those who don't know, the strong convergence of this operator would look something like this, where you act, it's still pointwise, you act on a set of operators in the Hilbert space, any operator in the Hilbert space, and then you take the Hilbert space null and then take
Sorry, but would this, I'm just saying, would this like the statement with the beta n?
Yeah, so this is strong, this is the strong operator topology. So I didn't say it, but this is this.
Okay,
this only makes sense
so
in the strong operator.
even though you only have the weak convergence up there, you get this strong?
Yeah, this is strong, yeah.
Okay.
Yeah, I didn't, details I didn't want to say, but yeah. Okay. So this is the strong operator limit. It's still a pointwise limit. But, yeah, you can square it and make it into the weak operator convergence statement, and then sort of makes sense. But anyway, yeah, so, okay, so, good. Okay. So this is the theorem we proved. So 1 is equivalent to 2 back and forth. So if you can do operator reconstruction in this sense, you have sequences of reconstruction maps, it works pointwise, then you have this sort of commuting with errors on the complement. And it turns out this is really important for establishing various theorems about the code. Like you can establish things like entanglement wedge nesting, and causal wedge is nested in entanglement wedges. If you know what these mean, I'll probably say something about it later, but you improve all sorts of things with these. So it's really important to have this theorem. If you don't have this theorem, you don't really have quantum error correction. Okay, so, and the other thing I should say is that this is a highly non-trivial theorem that we proved. It assumes something about this algebra, which I should state, which is that it's hyperfinite. It's a technical assumption. You still have type 3, type 2, type 1, hyperfinite monomial algebras. It just means you can approximate it by matrix algebras. And that approximation is very similar to what Ahmed is talking about with his projections. It turns out you can actually still prove this, a version of this, even when it's not hyperfinite. I won't go into details, but there's some things you have to drop. But okay. Good. Now, now the other thing that you might want is some sort of complementary thing. So this is called, I also didn't use the name, this is called complementary reconstruction. I was only just talking about this part in some sense now. What if we add this part to this theorem? Do we get something like the RT formula, which is what happened here? And the answer is, well, not really, because we don't have the RT formula necessarily, but we get something which is related, which is called the JLMS formula. So you can also prove the following. So this is called, so I'll call this theorem 2 that we proved. And it's the following idea. It's also, we have 2 conditions that are equivalent. So the first condition is that we have operator reconstruction, which just means we have one of the conditions in theorem 1, so 1 or 2. For a pair of sequences, mn and n, as well as their commutants. Right? And, right, so this is the complementary condition. We have both of these. That's equivalent to knowing that the limits of the relative entropies of states on the code, so from the physical states that you get by acting with Vn to make them as operators in the physical Hilbert space. This is just the bulk relative entropy for that algebra n. So clarifying things. So relative entropy is just some other thing like a von Neumann entropy, but it's generically defined in all of these von Neumann algebras, right? So in the type 1, so entropy itself can't be defined for type 3, but we can use relative entropy. So this is kind of replacing the Rutaki-Nagy formula. In the finite dimensional case, it's just this trace rho log rho minus log sigma formula. That's the relative entropy. There's some version for type 3 as well. Yeah, okay, so these 2 things are equivalent. So if we knew the relative entropy had this nice limit this is for all states, right? If we know that it has this limit, then we know we can do operator reconstruction and vice versa. Okay. Good. All right. So now, yeah. Okay. So because of time, I'm going to have to drop some things, but that's okay. I think I will go a little bit through how these codes are derived. So the idea is this is a framework that we just wrote down. Okay. It's some interesting math theorem about these VNs, but where does it actually come from? So can we actually derive a VN from what we know about ADS CFT? And maybe do we need to use a tensor network? And the answer is no, we don't need these tensor network models. We can directly derive a VN, and there's a procedure. So let me just go through that in a little bit of detail. So that will explain where some of these things come from. Okay, so you can derive such a code. And to be completely honest, there's a few assumptions about convergence that I will say when it comes up. Modulus and assumptions. And it's from the large N limit of matrix-like models. So it's quite general. It's probably more general than this. And just to preview, H comes from is a Hilbert space constructed from the single trace fields. And this non-isometric behavior in that case can be understood because at any given finite n, the single trace fields don't form an algebra. Okay? When you act with single trace fields, they'll eventually sort of take you outside of the single trace description, and so that means that at any finite n, they're not going to be very useful. However, if I fix the single trace field that I'm talking about, or the the correlation function with the single trace fields, at a sufficiently large n, it will be, the single trace description will be a good description of those operators. Okay, and so that's where the non-isometric, the sort of pointwise thing comes from. Okay. Good. So let's talk about the derivation of Vn. So the starting point is large N factorization. So that means that I have some set of single trace fields. So I'll label them phi n I, and each of these, for each I, you have some combination of traces like this of n by n matrices. And because there's a single trace, that's what we call it, a single trace. So that's one ingredient we need, right? But we also need a sequence of states, like some nice states, like the vacuum state, or something we're interested in, or a thermal state, some sequence of states that has a nice large N limit for these single trace fields, right? So what that means is that when I compute correlation functions, perhaps after subtracting 1-point functions, correlation functions in this state, in the limit, factorize. Right? So you get something like you get sort of Wick contractions. Phi 1, phi 2, phi 3, phi 4, and n, plus permutations. And then this is as n goes to infinity. So only as n goes to infinity does this happen, but yeah, so you get these sort of factorizations here. So in this context, we can define sort of a formal C-star algebra, which is a sort of an algebra of operators that is slightly different from a von Neumann algebra.
Finite n, so violations of factorization here, are they expected to be polynomial in n or exponential?
Yeah, so these will be polynomial, right? Yeah, so the interactions will be polynomial, yeah. So that's not something we're getting in this code. So to see that in the code, you would have to include 1/n corrections, which is something that's not beyond, you could probably state this theorem including 1/n corrections, but it's not something we did yet. So yeah. So, but that's what what I sort of mean when I say we're just getting small fluctuations about a fixed background. Yeah, so we don't see them one, yeah. Good. Okay, so now with these, so we sort of we think of phi I as formally the infinite n limit of these guys, and then you can easily construct a C-star algebra using these fields, these formal products of fields, modulo commutation relations that come from the state, right? So these are fixed, by this state here, and that defines some C-star algebra. Omega n defines a state on this C-star algebra. Once you have these two things, you get a Hilbert space using the GNS representation. That's a theorem. I should say this C-star algebra is a very particular thing. It's called the Weil algebra. Something you can write down. Yeah, so you get this GNS Hilbert space. Along with that, you define a sequence of maps. It's very natural. It takes one of these fields at infinite n and gives you the finite n representation of that field. Okay? So this is sort of, it's like an operator reconstruction, but it's kind of trivial. It's just saying this is some label for this field, particular field here, and so then just hand me this trace where these are the finite n matrices. Okay, and that's really what we mean by a single trace sector. We mean that for each n there's one of these operators, and that's really, yeah, so you sort of, that allows us to identify them between different theories. So this is an important map, but it's sort of clearly trivial to define. And then, using this, we define the map Vn just by acting on the GNS Hilbert space with some operator. That's this GNS representation of the operator n, just as the linear representation of this map gamma. So you can show this is well defined. It may be an unbounded operator. However, you can make some tricks to make it bounded, assuming some convergence condition. So that's where the assumption comes in. But under those convergence conditions, which are reasonable, you can show that Vn is a nice bounded operator, and in particular has this Vn dagger Vn to 1 pointwise property. So you derive this code. You also, along with it, derive a reconstruction condition, which looks like this, for this map gamma. And you should think of this as like the global reconstruction. This is like sometimes called global HKL reconstruction, if you know what that means. But yeah, you have that. Okay. All right, so I want to say that maybe a few more things. Can I have 5 more minutes? Is that okay? I think we started a little bit late, didn't we?
You have roughly 10 minutes.
Oh, how long is this talk?
No, we started late.
Oh, okay. I thought we started. Okay, so I still have 10 minutes.
I think so. Let's say 5 to 10 minutes.
Yes.
Okay.
I'm just kidding. No, yeah, well, 5 to 10 sounds good. Okay, so, good. Good, so we have this idea. Now, so that's fine, so you get sort of a map, you get a code out of this idea, but the really interesting thing about this code is when you talk about the local properties of this code. So let me talk a little bit about that now. So in particular, I want to emphasize that at no point did you see a tensor network or anything like that. So this just comes out of what we usually think about in maybe a CFT. Now another thing we can get is, if I think about the CFT, say we're studying a CFT for now, we're talking about local properties, so we're studying a CFT. CFT labeled by some parameter n, and we study it on the cylinder, right? So d dimensions, we can naturally put it on the cylinder. Then we can talk about observables that are localized to some region O, some causally complete region O. So if we draw some kind of causal diamond, then it's natural in algebraic quantum field theory, which is really the framework we end up using, to associate algebras to these kinds of regions. Right? So this is in lieu of these sort of tensor factorization between Hilbert space A, like so we have A complement. You might have said previously kappa is kappa A tensor kappa A complement, but we know these are kind of type 3 von Neumann algebras, so we can't do this, so we just have a set of operators, and that operator is those operators associated to this diamond. And so we can localize things to this diamond. And so in particular, we can take our boundary operators and localize them to O. That's what I mean by that. That's some subset of operators here. I can also localize the algebra that I get from these single trace fields, and I can restrict those algebra to O, and I'll define that as the von Neumann algebra C of O, and that acts on the bulk of its space. Then you can show under these conditions that gamma n still reconstructs C of O. Right? So C of O is going to be what we should think of as the causal wedge. It's sort of the stuff that's really easy to reconstruct. Because gamma n is a very simple reconstruction, so it's very easy to do that. And yeah, so good. Now, once we have that, another thing we can ask about is if I have O, let me unwrap the cylinder. Here's O. I can also think about the complement region, which is sometimes written O prime. It's just a set of points that are space-like separated to O. And I can ask, well, what is the algebra associated to that? Right? And there's an important result in algebraic quantum field theory that in many situations, not in all, but in many situations, this is the same as the commutants. This is just a set of operators M that commute with M. Sorry, this is M prime that commute with Mn. These things are equal, right? And so this gets a name. It's called Hard duality. And from like a lattice point of view, it's something we would always assume. It's basically all of the operators times all of the operators here is all of the operators here, right? Okay. I'm sorry. Let me say that more carefully. All of the operators and the thing that's generated by all of these is this guy generates all of these. So that should be the case. And so that's a reasonable expectation here. So I'm going to take that as an input. But with that as an input, you can now prove that one thing you can show is you don't necessarily have Hard duality for C, right? So we have now C, and we have C of O, and we have C of O prime, and we don't necessarily have Hard duality. So in the bulk theory, Hard duality can be violated. Duality violated for C, right? So what that means is that in general we'll have C of O, O prime is contained in C of O prime, but it's not equal to. And so the picture that you draw is that if you think, here's ADS, here's a time slice of ADS, and then you have some boundary region O, and here's the complement region. I'm not drawing time, so it looks a bit different. Then the causal wedge is somehow associated to some region in the bulk here, C of O, and then C of O prime is associated to this region, and there's a gap between, and that gap is violations of this equality. If we had equality here, we would go all the way up to there. And so this is a violation of Hard duality, and so this allows me to define what I mean by an entanglement wedge in these codes. It's just a maximal extension of the reconstruction maps from gamma n, which reconstructs C of O, and then O, to some larger reconstruction map, beta n, which reconstructs the entanglement wedge, which is a larger region, and then similarly for the complement.
Sorry, Tom.
Yeah, let me just, sorry. Yeah.
It's a statement that you have Hard duality on CFT and but not in the FN and algebra.
Yeah, exactly. Yeah, it's kind of like an anomaly, something like that. Something you don't get when you take the limit. So in the existence of entanglement wedge is some extension where this extension is maximal and satisfies Hard duality. Right. And this is something that may or may not happen. Okay, so it's just something we can't prove because there's some settings where it doesn't happen. And so it's just something you have to check and something you can try to prove in various situations. Okay, and so I'm going to finish here. I think I've sort of exhausted my time, but I had more things to say, and the other things that I had to say were just sort of some settings where you can actually prove this. And those settings are kind of interesting. There's one that's just sort of trivial and dynamical, but there's another, trivial and kinematical, and there's another one that requires sort of dynamical input about the code. And if you want to hear more about that, I can tell you more, but let me just finish there and see if there's questions.
Questions for Tom?
When you lose hack duality in this limit, do you expect to see emerging global symmetries?
Yeah, that's a great question. I think the answer is no, but I mean, in some sense, there's some definition of a symmetry, which is just an inclusion of algebras. I think that's what you're referring to, right? It's not my usual definition of a symmetry. Maybe it is for some people here, but not usually. But if you ask like Vaughan Jones before he died, that was his definition of a symmetry. And yeah, we have an inclusion here, the causal wedge inside the entangled wedge. But I don't really associate that inclusion with a symmetry. But maybe I'm wrong. Maybe there's some way to think of it that way. Maybe the fact that there is an extension means there's no symmetry, but maybe in some settings where there's no extension, there's some kind of, maybe you can think of it that way. Yeah, it's a good question.
Can you show that all these states where this pointwise convergence fails are these ones that you were worried about before, where you might form a black hole or something like this?
I don't know if show is the right thing. I mean, I can give some picture, but yeah, we haven't done any calculation with that. But yeah, the kind of thing that will cause problems is if I take, for example, I take some fixed state on the code, and then I act with some operator on the code, but I let that operator depend on end. Okay, so that's not part of what I'm allowed to do. But that's the kind of thing that might form a black hole. Right.
I guess I'm wondering, is there a state where this fails, which is not a black hole or something unreasonable in the bulk? It's actually, it looks maybe it's not so bad in the bulk, but this somehow fails.
Right, so I think certainly like there's some things where it's just like you have to include, like there's another perspective on this sort of 1/n perturbation theory, which is that's how you understand back reaction. And so there's some sense in which maybe this is just a small back reaction, and I can understand that from perturbation theory, but the codes here won't be able to track that. So yeah, I think maybe that's the setting, where you're talking about. And it would be interesting to connect those things more sort of mathematically. I mean, like for example, like I can act with some single trace field like this. So like this. And if I let the amplitude grow, then that will do something that might change the geometry, maybe just a little bit, and then.
Yeah, on the bulk side, are you worried about the formation of a horizon or something, or?
Well, that's the more interesting case.
Right.
This is like kind of a dumb
Yeah, exactly.
case.
So
Yeah. So this I think some of these things can be treated in perturbation theory, which we haven't done yet, but in principle, yes. Yeah. But probably. There's also this question of complexity, right? So I think these codes are some sense sort of order 1 complexity. The perturbation theory is sort of like polynomial complexity, and then the really interesting stuff is exponential complexity. Maybe that's more related to black hole horizons. It would be nice to have some understanding of this complexity story of these codes, which I'm not summarizing, but in terms of quantum field theory, I think we don't have that, and if we do, then we'll have like a better understanding of this.
I have 2 questions. The first one is in your theorem 2, if you include 1/n corrections.
Yeah.
Sorry, it's not on the board anymore, but it's
Yeah, theorem.
there were 2 entries where the JLMS condition is equivalent to
Yeah.
operator
Can you
reconstruction.
explain the theorem 2 again?
Oh, it's,
Yeah, let me, it's like you have there's two conditions that are equivalent. One is operator reconstruction for Mn within and the commutant. You need both reconstructions. So that's this hard-dual setting. I didn't say that, but that's exactly the setting. Then this is equivalent to knowing that this limit converges for all bulk states. There's some technical thing that I didn't tell you, but I don't think I need to talk or for your question.
yeah, in the finite dimensional version of this
Yeah.
theorem, there's like this
Correct.
equivalence also with the RT formula. But I was wondering if you could promote this theorem too by adding 1 over n corrections.
1 over n, yeah, I would love to do that. Yeah, I think probably could, yeah. But yeah, this is a strict infinite, and so it doesn't see those. So that would be a thing to do. I think it would be come together with trying to understand this sort of how to patch together different codes.
Yeah.
Like what we were just talking about. So yeah.
And then my other question was, do you expect non-hyperfinite algebras to be relevant?
We have examples. Unfortunately, we have examples. So I don't know. I never thought that would come up, but now there's like at least 2 examples of hyperfinite things that have arisen.
Non-hyperfinite.
Sorry, non-hyperfinite things.
What are they?
Like these double scale SYK, the type 221 algebras there, apparently non-hyperfinite. And this free product.
Oh.
That is not a hyperfinite thing. So,
Thank you.
All right, if there are no more questions for Tom, it's time for a good talk.